Hey, this is Jake Stimson. Just going to go over Lab 8, where we use the Neon SIMD processor on the A9 to parallelize our filter operations and then decrease the time, the frame time for each processing action. So here we have just the pipeline that we've been using since Lab 5. We have our HDMI in that's connected to our receive constraints. Then they take this data and convert it to our 24-bit RRGGBB data, which then gets converted to 32-bit and gets stored in our VDMA, and then reconverted back from 32 to 24 and outputted via our HDMI out, which is connected to our HDMI transmit pin constraints. So this is just the hardware pipeline, and it's the one we've been using. But so going now to Vitis, here you can see we've implemented our filters. Here I have a sharpen filter, so this is one I implemented in Lab 7, and now we're just using, the unsigned int 16x8 data types that are in the Neon processor to kind of parallelize all these operations. We're doing the same thing with the Gaussian blur, so I ported these two over from Lab 7 and rewrote them into using Neon data types. And then here we have the existing pre-wit filters that were included with our lab from our professor here. So yeah, everything works. In general, right, the things that we had to do where we had to modify our V7 GCC compiler miscellaneous flags. So we had to flag that the processor we want for our floating point operations is going to be the Neon VFPV3. So this selects it, and then in the linker, I believe it's in the in the options for the GCC compiler, optimization here. We do f unroll loops and ftree vectorize, right? So this tells the compiler to optimize our C code when it's actually compiling and linking. Then just like the other labs, right, we brought in our platform component that contains our hardware XSA file. So this has all of our device tree, and when we build this, it'll create the xparameters.h that we can then reference in our C code to access all of our devices by their base address and their device ID. So we built this. I've actually included an HDMI 1080p version of this hardware design, which modifies the DVI to RGB block here by selecting this 1920 by 1080p option. I'm not going to save that now, but that just allows us to get the full pixel output on my 1920 by 1080p monitor rather than a smaller portion of it, which you'll be able to see in the short that I posted, which shows the outputs for this lab. But yeah, in general, everything works. I'll just reflash, bring up a PuTTY terminal really quickly, open it to COM12, which is where my board's at, and then I'll rerun this system configuration. So you'll see that the UART port will, or the UART interface will come up, and when I select 9, we have the Neon Gaussian filter and the Neon sharpening filter cases that I've added. So you can see, I mean, it's super simple to add these, but in general, you'll just go up to the function that handles our case switching, right? So here I added these two cases, and it just disables cache, selects the next frame, stops video capture, and then calls the function with all of the frame dimensions and the frame pointer. So the same as all these other ones, and of course we added the xilinx_printf statement here so we can actually show the user that these new options are available. Yeah, so in general, everything's working. Look at the short if you want more information on that. Yep, thank you. Please give me a good grade.